Now what if we want to estimate the mean and estimate the mean we want to estimate mean, and instead of having a number, we want to control for the relative absolute error. What does that mean is that we do want to estimate the population mean y bar, and we will take a sample by SRSWOR of the size n. But instead of stipulating a k of say 0.5, we are now stipulating the absolute margin of error, that is y bar minus y, and that should not exceed a fraction of the population mean. So this has to be less than k of y bar, where k is a fraction of say like 0.5 or 0.1. So that would be a fraction of the population mean. So then what that k becomes y bar, small y bar minus big y bar, absolute value divided by y bar. So this is the relative absolute error, right? This is the absolute error, this one is the absolute error, and this is the divided by the mean. It becomes a relative absolute error, and we have stipulated that it has to be less than a certain value. Now this is what we have: y bar minus capital Y bar is less than k y bar. Okay, this is what we want, but we are talking about a probability sample, right? We are talking about probability. So we can require that for some error rate or some confidence limit, 95%, with 95% confidence, that the absolute error, which is this, lies within k times mean. So we cannot be 100% sure of anything, but we can say that we want to be 95% confident. So that is 1 minus alpha. So probability that y bar minus y hat is less than k y hat is more than 1 minus alpha, which is basically 95%, or it can be 99 or anything, but it's a confidence limit. So this is what we can say: probability of y bar, probability that the absolute error is less than certain limit is more than 95%. Now there are two ways we can further proceed from this. We can assume that this difference is normally distributed. The y bar minus y hat, or absolute difference, is also a random variable which is normally distributed like this. So if it is normally distributed, and for example we have this point over here, so this point's value is going to be, what is the value of this point? This point's value is z half times sigma y bar, that is this point's value. And we want this point to be, we want our y hat minus y bar to be less than this point, this value, this absolute value, to be less than the value of this point at a probability of more than 1 minus alpha. So we want this whole thing to be more than 1 minus alpha, and that is the value of this point. So now we have two equations. We have this equation over here and this equation over here with normal distribution. So then from that we can get ky bar is equal to, because this is the same here and here, ky bar is equal to z half sigma y bar, and then you can solve from here, because then you can do zy by s. Sigma y bar we know is s upon under root n 1 minus n upon n, and then we can keep solving this with algebra to get this sample size calculation, which is going to be CV z half upon k square upon 1 plus 1 minus n CV z half upon k square. And what is CV? CV is nothing but coefficient of variation, which is population standard deviation divided by the population mean. So that is one way of solving this. But what if we cannot assume that this is normally distributed? Then we cannot use this little thing here. But then there is something called Chenkov inequality, and we use that and come up with and that's too complicated to get into, but we can calculate the sample size, which equation is going to be 1 upon alpha k upon CV square, where CV is s upon y bar.